Hello, AP Chemistry students. In these notes, we're going to do two sets of notes. We're going to cover intermolecular forces and what they are, and then we are going to get into properties impacted by intermolecular forces. As a warning for this video, you need to be able to determine the polarity of a molecule before you start getting into intermolecular forces and things of that nature, because intermolecular forces are totally dependent upon the polarity of a molecule. And so if you haven't done those notes or you feel like you don't understand polarity, you need to first get that worked out before you move on to these notes. Intermolecular forces you almost certainly have talked about in either other chemistry classes, but definitely in first year chemistry. And I don't know the depth that you went into, but this is going to be a huge topic for the College Board as they are writing your AP chemistry test. What we've been discussing thus far in this unit are really intramolecular forces. The prefix intra means within, and so these are talking about actual bonds. What we're discussing today is something called intermolecular forces, and we've kind of seen that the prefix inter means between. And so intermolecular forces are not the bonds, because they're actually going to be between different molecules, and these are going to be the attractions that hold molecules together. So chances are you are writing in your notes packet, and as you write on your page, on your paper, the paper doesn't just break, okay? But what you could do is you could get frustrated at the notes packet and you could hold it up and you could tear it in half. When you do that, you're not actually breaking any of the chemical bonds within that paper. Both of them are still paper. That is not a chemical reaction. Instead, the strength of you ripping your pages would just be breaking the intermolecular forces, or the forces that hold those paper particles, that cellulose in that paper, together. There are mainly three types of intermolecular forces that you need to be really, really good at. And then there's a fourth one called ion dipole that we'll discuss, but it doesn't seem to be this huge intermolecular force in terms of the AP chemistry exam. So what I'm going to do is I've kind of summarized it on this page. And then I've kind of talked a little bit about ion dipole, but what I want us to do is maybe move a couple pages ahead here. And I want us to summarize it kind of in our own words. So the first intermolecular force that I'm going to cover is going to be London dispersion forces. Now, London dispersion forces are sometimes called dispersion forces. And oftentimes, in the world of chemistry, it seems like almost everybody uses the term LDFs. Maybe you've even heard of them before. So some important notes to know about London dispersion forces is, first, all molecules experience London dispersion forces. In general, LDFs are weak. However, LDFs become very strong in large molecules. And I'm going to even say in very large molecules, because, like, for example, when we draw Lewis structures, if you had something that was like C4H10, that might feel like a large molecule, but in the world of chemistry, that's still a somewhat small molecule. So I'm talking huge molecules, maybe like 100 carbons and 200 hydrogens. And so there's a general rule of thumb that the more electrons you have, that will equal stronger LDFs. Okay. So the question right now is, what the heck is a London dispersion force? And so let me answer that. A London dispersion force is simply electrons in one atom or molecule attracted to protons of another atom or molecule. So the picture I like to draw is we've got maybe a nucleus here and we've got some energy levels, and let's say I put an electron on one of the shells. This attraction force is not a London dispersion force. This is an intra or within molecular force, intramolecular force. However, even when you have a really, really tiny sample, you can never have just one atom. And so there are neighboring atoms. So in green here, I'm going to draw the London dispersion force. If you look, see how this is between two different atoms, could also be between two different molecules, how it's the electrons in one atom, this guy, attracted to the protons of another atom or molecule. And so in green here, this is our LDF. Because all atoms have protons and all atoms have electrons, that is why this is in all atoms and molecules, or that they all have this kind of intermolecular force. Additionally, we wrote that more electrons equal stronger LDFs, and because this is only one electron that I just drew, imagine if you had many, many, many electrons and then many, many, many protons, that these forces can become quite strong. Now, other names for this that I just was thinking of as I was writing this that your AP test might use is a London dispersion force is considered an induced dipole. And a London dispersion force is also considered temporary. The reason that it's temporary is that electrons are constantly moving. And so because they're constantly moving, this attraction that we've kind of highlighted is constantly being broken and formed. That is London dispersion forces. Everything's got them, and they are, in fact, temporary. The next intermolecular force that I want to discuss is called dipole-dipole attraction, or dipole-dipole forces. And the reason I gave the warning at the beginning of the video and why you need to be able to figure out polarity is dipole-dipole forces are found between only polar molecules. Polar molecules have electron density spread unevenly throughout the molecule. That means one side of the molecule could have what we call a delta positive side, and it would simply be attracted, let me reword this, delta positive in one molecule attracted to delta negative in another molecule. So this is generally pretty strong. And this might even be called a permanent dipole. Okay, so here's an example. I could have HCl. We learned last class that hydrogen's electronegativity value is 2.1. Chlorine's electronegativity value is 3.0. And as a result, electron density in this bond is pulled towards chlorine, and that gives chlorine what we call a delta negative or a partial negative, and hydrogen has a partial positive. Well, whenever you have a sample of HCl, you have many, trillions of these molecules. And so you have two possible scenarios. One is that HCl could align itself like this. The other is that HCl could align itself, like this. Okay, so we could say this could be the dipole, or this could be the dipole-dipole forces. Hopefully you're saying as you're writing this that it's got to be the top one. Because if this hydrogen's delta positive, because this is just simple math, this hydrogen has also got to be delta positive and this chlorine's delta negative. Because of Coulomb's law and the idea that opposite charges attract, this is our dipole-dipole force. Notice that when I draw these London dispersion forces or dipole-dipole forces, I'm using dashed lines because they're not chemical bonds, they're just chemical attractions. And so we use dashed lines to indicate the difference between an intermolecular force, which is what the dashed lines are, versus an intramolecular force, which is what our covalent bonds are. Another scenario could be, let's say I dissolve HCl in something like methane. Okay. Or I try to, I should say. HCl is still a polar molecule. It's got its delta positive, it's got its delta negative. But if we go through and we look at the electronegativity of hydrogen and carbon, we would say that their difference in electronegativity is only 0.4, and that's not enough of a difference in electronegativity to consider this a polar bond. As a result, we would say this has no dipoles. And so these guys are considered insoluble in each other. They're considered insoluble because they cannot form dipole-dipole attractions with each other. A great example of this would be two immiscible liquids like oil and vinegar. Oil is nonpolar, vinegar is polar, so the dipoles in vinegar have no way of forming dipoles with the oil, and therefore they're considered insoluble. What is soluble, though, is like, let's say we try to dissolve HCl in something like cyanide. Okay, solubility has nothing to do with single bonds versus triple bonds. Let me get some lone pairs on here. That way the Lewis structures are correct. And we've seen that hydrogen's delta positive, chlorine's delta negative, carbon is 2.5, nitrogen is 3.0. So actually, nitrogen's delta negative and carbon's delta positive here. And as a result, these opposite charges are going to have attraction towards each other. And that attraction is considered a dipole-dipole force. So because these guys are able to form dipole-dipole attractions, we would say that they're going to be soluble in each other. You can dissolve hydrochloric acid in cyanide. And so they're soluble because they can form dipole-dipole attractions with each other. Okay. Now, our last one that we're taking notes on here in terms of intermolecular forces is going to be hydrogen bonding. And you may say, Mr. Payne, you didn't leave me very much room on my page, and that's okay, because hydrogen bonding doesn't have too much, and we've kind of already discussed it without knowing it, maybe. On a test, on a quiz, you are welcome to abbreviate hydrogen bonding as H bonding. Hydrogen bonding is considered just extreme dipole-dipole. And so here's what I always teach my students. Instead of calling hydrogen bonding fun, F-U-N, think about it as FON, F-O-N-N. Only these three elements are able to cause hydrogen bonding. That is what I'm saying there. So let me give you some examples. If we had HF, we could go through and figure out some electronegativity values, 2.1 and 4.0. You might say, like, whoa, that difference is going to be 1.9. That's a strong difference. That's borderline ionic. Okay, if we go back a couple pages, and let's see, actually not in these notes, but a large difference in electronegativity is going to lead you to actually cause not covalent bonds, but actually ionic bonds. And so this is right at the border there. So we would say that the fluorine is like super delta negative, leaving the hydrogen super delta positive. Similar to the example with HCl, you never have one molecule of HF, so we'll put in another molecule, and we'll consider both scenarios. Here, hydrogen's still delta positive, fluorine's still delta negative, fluorine's still delta negative, and delta positive. Our scenarios are that this F could be attracted to this F, or this F could be attracted to that H. Hopefully you say, Mr. Payne, by now I know that opposites attract, so these guys are going to have attraction to each other, meaning this guy is not reasonable, and so this attraction between them, this is our hydrogen bond. Now, this name of hydrogen bond is a poor name because it is not a covalent bond. Instead, it's just a really, really strong extreme dipole-dipole attraction. The other scenarios for hydrogen bonding might be something like O connected to H. There, we still create, with 3.5 and 2.1, a very strong dipole. So this is still very delta negative. This is still very delta positive. And our last example would be N to H, where it's still very delta negative and still very delta positive. What's kind of cool with all this is if we think about solubility, you learned in Unit 1, hopefully you memorized some of your solubility rules, is water is kind of the poster child for a molecule that can hydrogen bond. That's because we get dipoles that point towards our oxygens, leaving us with a net dipole going up like this. As a result, oxygen's highly delta negative, or hydrogen's highly delta positive. So you could have two scenarios, and I'm just going to make up some molecules. We could have nitrogen that has some hydrogens, maybe like ammonia. We'll do that. And we could compare that to something like, let's see, H2S. In both of these are polar molecules. And because water is polar, if you use the idea of like dissolves like, you would say, oh, they should all dissolve in water. But solubility is not just a yes or no kind of idea. It's more of a continuum. Which of these, ammonia or H2S, which is called hydrosulfuric acid, should dissolve in water the best? And there is a clear answer. Think about what it might be, ammonia or hydrosulfuric acid. Which one should dissolve in water better than the other? And the answer that I hope you come up with is ammonia. So you might say something like, if you were forced to explain that, since NH3 and H2O both contain hydrogen bonds, since NH3 and H2O both have H-bonding IMFs, they are able to H-bond with each other. Because they can form, you don't have to write all this, but I'm just going to explain it. Because they can form strong IMFs with each other, they will be soluble, or most soluble with each other. Then I'll change it to pink because I'm going to now talk about H2S. Since H2S does not have H-bonding IMFs, it cannot H-bond with water and can only form dipole-dipole forces with water. And I would just say, since this is a weaker interaction, this results in just less solubility in water. Okay, so I know I've written a lot on this page. I hope it's been helpful. Let me show you, and I might use green again. So this would be a hydrogen bond between ammonia and water. And if we had another NH3 molecule, maybe like HN, NH, something like that, this would also be a hydrogen bond. So notice it needs to be N attracted to H, N in one molecule that has H's attracted to another H in another molecule that's attracted to F, O, or N. Now, if I drew H2S, we could do HSH. I'm going to use, I guess I'll use pink. This is an attraction. This is just a dipole-dipole attraction. And by definition, if it's just dipole-dipole and not the extreme dipole-dipole, which we call hydrogen bonding, that regular dipole-dipole attraction is just weaker. Because they're forming weaker interactions with each other, they will have less solubility in each other. Okay, let's go through notes 8. At one point in this, I'm going to have you pause the video and draw some Lewis structures. But I want you to think about phases of matter. We've got gases, we've got liquids, and we've got solids. And you should know that solids have the strongest intermolecular forces, where gases have the weakest. We even said in the gases unit they kind of have no intermolecular forces so long as they're very far apart from each other. What I discussed in the previous notes is the idea of like dissolves like. And so all that means is that polar compounds dissolve other polar compounds, and nonpolar compounds dissolve other nonpolar compounds. You can think about it as kind of like a black and white scenario, but it's very much not black and white. Sometimes solubility is not clear cut. Okay, so now let's discuss boiling point and melting point. If we look at these guys, these are all true hydrocarbons. When I say the term true hydrocarbons, oops, and I wrote that wrong, hydrocarbon, that means they are composed of only C and H. And when that happens, they are always going to be nonpolar. So here I have something called butane. Here, this guy is called hexane. This guy is called octane. At first glance, you might be like, oh, they're all nonpolar. And that is true. But if we look here, and this appears to be their melting point, why are their melting points so different? Well, this is a London dispersion forces thing. Because they're all nonpolar, that means they only have LDFs. And if we think back to what we wrote about LDFs, we said LDFs can be dictated by the amount of electrons something has. So because this has less electrons, and this one has more electrons, having more electrons means that the electron cloud is more polarizable, and that means you will have more possibilities for electrons in one atom to be attracted to protons of another atom. I'm going to save distillation for when I am there. Distillation is something that we do all the time in organic chemistry, and essentially all it does is it separates things based on boiling point, but we will do a lab where we do distill. And then surface tension is the resistance of a substance to increase in surface area. And so the stronger your intermolecular forces, the higher your surface tension. A good example of this, in this picture is going to be a little bit cruddy, is imagine I have a bug, and I know he's ugly, but that's my bug, and he's walking on water. He is exerting a force down, but our water molecules are held together, not by chemical bonds, but rather held together by intermolecular forces, specifically hydrogen bonding if it's water. And so, because this is such a strong intermolecular force, we see on the macroscopic world many small animals be able to walk on water because they must not be exerting enough force to actually break the intermolecular forces. However, if you take Mr. Payne, and again, I'm going to ruin this picture. Mr. Payne weighs a lot more than a bug. You should probably know that. And so the forces that I would exert on water are going to be, orders of magnitude greater, and that's going to break those intermolecular forces because even though intermolecular forces can be strong, they're not as strong as chemical bonds. And so when you break the surface tension, you're not breaking chemical bonds. So we're going to say you break the surface tension, you're not breaking chemical bonds. Instead, you are simply just breaking the intermolecular forces. By definition, intermolecular forces are much weaker than the actual chemical bonds. One thing that's going to be helpful, I think, for students to kind of memorize, and so I'm going to write this here for you to also write, and you can put flashing lights around it because it's that important, is when you have strong intermolecular forces, this generally means you are going to have high, and then I'm going to say insert physical property. Some examples of this. If I have strong intermolecular forces, that means I have a high boiling point. If I have strong intermolecular forces, that means I have a high melting point. If I have high intermolecular forces, that means I have a high surface tension. If I have a high or strong amount of intermolecular forces, I'm going to have a high viscosity. Viscosity is the resistance to flow. You might have heard of like honey before. If you try to pour honey out of a bottle, it's very viscous. That means the actual honey particles are held together very strongly by intermolecular forces, and so they don't flow nicely. However, every good rule seems to have an exception, and that exception is vapor pressure. So, you may remember that the vapor pressure is how much of your liquid substance or gas or solid substance is in the gas phase above its liquid or solid phase. So we have these two scenarios, flask A and flask B. Hopefully we agree flask B has the larger vapor pressure. And all that means is more of B is in the gas phase. Because more of B is in the gas phase, that must mean that B has weaker intermolecular forces, assuming these are at the same temperature. The weaker somebody's intermolecular forces, the greater the likelihood is that that substance will be a gas. And because of that, that is why this exception. High vapor pressure means you have a lot of gas, and when you have a lot of gas, you do not have strong intermolecular forces. Okay. On this last little bit of the notes here is I want to look, and we'll do probably the end of the notes when I return, but I'm going to have you pause in just a second, or you can follow along because I'm going to draw the Lewis structures here. I'm not going to fret too much over lone pairs of electrons unless they're on a central element. I think that makes it much simpler for us to analyze polarity. So take a second and draw these. Okay. Once you've got those drawn, I'm going to go through some things here. We just want to predict which substance from the following pairs will have the greater intermolecular force and explain. So we need to be excellent at being able to determine polarity. I would look at carbon dioxide, and while there are dipoles going this way, they both cancel, so there's no net dipole. So I'm going to call this NP, nonpolar. When we get to OCS, oxygen's 3.5, carbon's 2.5, and sulfur is 2.5. So we just get a single dipole arrow going this way. That makes this guy polar. Something that's nonpolar is going to have LDFs, and that's it. Something that's polar, like this guy, is still going to have LDFs. But because it's polar, it's going to have dipole-dipole. Ask yourself, OCS, does it have hydrogen bonding? And the answer is no. So this is kind of what we're comparing. Before we actually compare them further, I want us to think about like London dispersion forces. And we said earlier in the video that if something has more electrons, it's going to have greater London dispersion forces. So I might move this over just a tad. And I might say that because this one has sulfur, which occupies more energy levels, we can assume that it has more total electrons, that this is going to be more LDFs. As a result, I would argue that the one that has a greater intermolecular force has got to be this. And I'm using these as kind of my rationale. As a result, then, if we were to compare OCS and CO2, we know that OCS has a greater boiling point, melting point, surface tension, viscosity, essentially any physical property, excluding vapor pressure. When we get to this next one, fluorine is 4.0, phosphorus I believe is 2.1. We're going to get some dipoles here. And we're going to get a large dipole pointing up. I believe that this makes this one polar. On PF5, we get some dipoles like this. And right now I've made my Y formation, so I know that the arrows on PF5 that I've drawn will cancel. Additionally, in this trigonal bipyramidal, left and right fluorines cancel, so this is going to be nonpolar. Because this first one is polar, I know it has LDFs, and I know it has dipole-dipole. I also know that it does not have hydrogen bonding because it does not have H connected to the F that is there. Now, when we look at this one, we know it has LDFs, but you've got to be able to say PF5 has more LDFs. So between PF3 and PF5, which one would you say has the greater total intermolecular forces? I think I would say PF3. However, is it possible that PF5, that its total LDFs could be greater than both the LDFs and the dipole-dipole of PF3? And the answer is yes. That could be the case. That would kind of be, it's not that it's an exception, but it wouldn't be something that we would necessarily predict on our own. So I want you to just kind of think, if something has more total intermolecular forces, you should be predicting that it has greater intermolecular forces. That is generally going to be true. There are exceptions, but the exceptions are not super common. On this next one, we have SO3. We end up having some dipoles, but they all cancel because they form that Y formation. So this is going to be nonpolar. SO2 has dipoles, it's in a Y formation, but due to the singular lone pair on the central S, this one is actually going to be polar. When that happens, we know they both have LDFs. SO3 has more LDFs due to having more total electrons, but SO2 is also going to have dipole-dipole. Similar to the last one, our prediction would be that SO2 has the greater intermolecular forces. However, if data was to prove otherwise, we would then know that it must be due to the LDFs of SO3. But our prediction is still SO2. On this next one, we get HF. F is 4.0, H is 2.1. Bromine, I believe, is 2.8, hydrogen is 2.1, so we both get dipoles pointed towards our halogen. I would just argue that the dipole in HF is much larger. Because we have a singular dipole that does not cancel, both are considered polar, so they both have LDFs and dipole-dipole. Bromine, being larger than fluorine, we would say has more LDFs, and it has dipole-dipole. However, this is the first one of the 4 that we've done, where I would also say because H is connected to F, we would also classify this as H bonding. As a result of HF having LDFs, dipole-dipole, but H bonding, which the other does not, we would make the prediction that HF should have the greater intermolecular forces, leading to higher boiling points, viscosity, surface tension, all the physical properties excluding vapor pressure. Okay, we got 2 more in this video. Stick with me. We look at CH3OH. We are going to get a net dipole pointing up. We get some other dipoles going this way, which is fine, but the net dipole is the first one that I drew. And then on H2CO, that is your net dipole. So they're both polar. The fact that they're both polar means that they're going to have LDFs and dipole-dipole. This one is composed of C and O. C and O. This one has 4 total H's. That's called methanol, where this one only has 2. So I think just barely does the first one have more LDFs. But what does the first one also have? We can see that they both have O and they both have H. However, for us to classify it to be hydrogen bonding, we need the O to actually be connected to the H. As a result, we would say only this first one has H bonding. And that leads us to predict that the first one has the greater intermolecular forces in total. Congratulations, we have reached the last one that we're going to do in these notes. And I didn't draw the Lewis structure on this one, but you're welcome to draw it. We have C, C, C. And then here we only have 2 C's. Then we have this NH2 group and an NH2 group. So the part that I've circled is kind of similar. And then I'll circle this part in green. This one has an extra NH2 group. I would argue if you didn't do any counting and you just kind of looked at the formulas, carbon and nitrogen are neighbors on the periodic table. So I would say that these guys have very similar LDFs. They're approximately the same size. You could go through and count and figure out which one had just a few more electrons, but I don't think that that would make much of a difference in the macroscopic properties of boiling point, melting point, surface tension, viscosity. However, what do you notice they both have? They both have hydrogen bonding. We can see that the N is in fact connected to the H, and here the N is connected to the H. However, hopefully you're saying, Mr. Payne, the one on the right has got 2 instances of hydrogen bonding areas. And as a result of that double hydrogen bonding areas, that's going to result in stronger physical properties. Okay, I think that's enough notes for now. We'll do the rest when I return. You can work on your skill sets that are related to intermolecular forces, and here's my recommendation. You're going to need to draw some Lewis structures, okay? To draw the Lewis structures, I know it takes some time, but that is going to be the best way for you to see the possible polarity in